Hello! In this video, we will be tackling problem number 1 of problem set topic 8A. In problem number 1, we are asked to describe the features of the solution of the particle in a one-dimensional box that appears in the solutions of the particle in 2 and 3-dimensional boxes. Furthermore, what concept applies to the latter but not to a one-dimensional box? To answer this question, we first consider a particle trapped in a one-dimensional box as illustrated below. Now this box here has one end placed at x equal to 0, and this box has a total length of n. On one end of this box, you see that you have a wall here that is defined by having a potential going all the way up to infinity. At the other end of the box, that is to say at x equals to L, there is a second wall wherein the potential also goes all the way up to infinity as well. Between x equals to 0 and x equal to L, the potential is 0 everywhere. The wave function for this particle is given on the screen. Now, applying Euler's identity, as shown on the screen, we are then able to get rid of the exponential terms in this equation and replace it with merely cosine and sine terms. This gives us the following equation for the wave function. Now, since a and b are both constants, we can then replace these terms in here, with new constants, thereby making this equation a whole lot simpler to look at. For instance, a plus b can be replaced with a new constant c, and the quantity I times a minus b can be replaced by a second constant b. Continuing the solving of the equation of the wave function, we next apply the boundary conditions of this problem, which are as follows. The two boundary conditions state that our wave function will go all the way down to 0 as x becomes less than or equal to 0, and also when x becomes greater than or equal to L. That is to say, the wave function will have a 0 value everywhere outside our box. From these two boundary conditions, we now arrive at this particular equation on the screen. Notice here that the cosine term has disappeared. The reason for this is that cosine, when x equals to 0, will have a value of 1. And our boundary condition clearly states that at x equals to 0, the wave function must be equal to 0. That's the reason why this term here disappears, and we're left only with the sine. Furthermore, it must be noted that the k value has been computed here. K is then equal to n pi over L. L, of course, is the length of the box, and the variable n represents the transitional quantum number. Now, to further be able to find all of the values necessary for our wave function, we finally solve for the value of b by normalizing the wave function using the integral shown on the screen. Through normalization, we then find the value of d to be equal to square root of 2 over L. And our complete wave function is the following. Using this wave function, we can then find the equation for the energy of the particle in a one-dimensional box. And its equation is shown on the screen right over here. Continuing on, let us now consider a particle in a two-dimensional box as illustrated below. In this particular illustration, our box has a length L sub 1 on one side and L sub 2 on the other side. Notice that on each side, the potential goes all the way up to infinity, thus forming the wall of our box. Finding the wave function of the particle in the two-dimensional box is a little bit different. The wave function of this particle is simply equal to the wave function of this particle along the x-axis times its wave function along the y-axis. Now it turns out that the equation for the wave function along the x and along the y have the same form as what we have found in the previous slide. Taking note of that, we then find that the equation for the wave function of the particle in two-dimensional box is now the following. As for the energy of the particle, its energy is equal to the sum of E sub x and E sub y. Now E sub x and E sub y both have similar forms as what we have found or derived in the previous slide as well. Taking that to heart, we then find the equation for the energy of the particle in a two-dimensional box to be equal to the following. Now for a particle in a three-dimensional box, it is derived in pretty much the same way, so that the equations for the wave function and the energy are summarized below. For reference, we have the equations for the particle in a one-dimensional box all the way at the top. Now the features that are common across the one-dimensional box, the two-dimensional box, and the three-dimensional box are that the wave functions and the energy are all variables of the transitional quantum state n and the length of their boxes n. This is true for the one-dimensional box. For the two-dimensional box, we see the same as well. The wave function is in terms of n and l, and the energy is the same. They're also in terms of n and l as well. The same is finally true for our three-dimensional box. The wave function and the energy are all in terms of the values of the variables n and l. Now, apart from the values of n and l, all other features of the particle will remain the same for any of these three boxes. Now, one particular characteristic, or one particular property that is applicable to a two-dimensional box and to a three-dimensional box, but not to the one-dimensional box, is the concept of degeneracy. Degeneracy simply refers to the fact that you can have two different states with two different values of n having the same value of energy. For a one-dimensional box, our energy is just given by the following, whereas for the two-dimensional box, it is equal to the sum of E sub x and E sub y, thus allowing us to have more than one state that has that particular energy that we can compute. The same is true for our three-dimensional box. The energy of the particle is the sum of E sub x, E sub y, and E sub z. Because of this, we can now have more than one state having the same value for the energy. Now, the degeneracy is commonly a function of the symmetry of the system. So, for instance, in a two-dimensional box, if the box is in the form of a square, and for a three-dimensional box, if the box is in the form of a cube, you can expect that there will be a degeneracy that we can find in this particular system. The same cannot be said for the one dimension.